In this question, we've been told that the heights of a population of women are normally distributed with a mean, an unknown mean right now of mu, and a standard deviation, unknown standard deviation of sigma. It is, however, known that 30% of the women are taller than 172 centimeters and 5% are shorter than 154 centimeters. Part A of the question asks us to sketch a diagram to show the distribution of heights represented by this information. Now, I would have wanted to draw a diagram anyway, but if they're going to give us some marks for it, we'll take those marks. So I'm just going to start by defining this distribution, mu and sigma squared, and then here's the sketch. So the standard bell curve, and we're just going to label mu in the middle. Okay, so where are these values going to go? Now, the tall women, 172, there are 30% taller than that. So 172, and I've got 30% off in this region. Shorter women over here, 154, only 5% are shorter than 154. So I've got both of these labeled on the diagram, and I've also annotated the probability or proportion that belongs in each of these two shaded regions. Part B of the question asks us to show this expression. There's a combination of mu and sigma, and I can see it uses the 150. Now here, without being told, we should know that we need the standardization formula. This is what links our z-score, our mean, our standard deviation, and our real-world value of 154. So I'm going to start off by giving us this fact in mathematical notation. The probability that x is less than 154, 0.05. I need the z-score that has 5% below it. So I can say that 5%, and I can look this up in the tables or on my calculator using the inverse normal distribution function. I'm putting in the probability on the left, and then the standard deviation, and then the mean. And for the z distribution, we know that those are 1 and 0. Okay, that gives me a z-score of negative 1.6449. I'm going to add this to the diagram. The corresponding z-score for 154, negative 1.6449. Well, that's going to go into the standardization formula. I can substitute this z-score. I can substitute the x value, the real-world value, the real-world height of 154. And I should be able to rearrange to get the expression I've been asked to show. So, rearrange, making mu the subject, and we get exactly what we were asked to show there. In part C, we're asked to obtain a second equation and to find the value of mu and sigma. Okay, well, we worked with the value 154 and we managed to produce one equation. We're going to do a similar thing for 172. I want to know the probability below there. Well, there's 30% above, meaning there's 70% below. I can use my inverse calculation again to find the z-score that matches 70% being below, and that's 0.5244. Okay, so once again, I have a corresponding z-score and real-world value. 172 corresponds with 0.5244. Okay, into the standardization formula, and in a similar way, we're just going to substitute, rearrange, and we could make mu the subject. Okay, so at this point, we have two equations, both of them mu is the subject. We could equate them and solve for sigma. But we actually have a simultaneous equation solver on our calculators. And I would rather rewrite these in a standard simultaneous equation format with the two unknowns on the left and a constant on the right. And then we can just substitute these into the equation solver. Whichever technique you use, we get that mu equals 167.6 and the standard deviation is 8.3. We found both mu and sigma. Finally, in part D of the question, we're asked to find the probability that a woman chosen at random is taller than 160. Well, this is just a cumulative probability question. Now that we know the actual distribution we're working with, let's get this on the diagram. We know that the mean, or mu, is 167.6. 160 is going to be over on this side, and we can just calculate that using our normal distribution cumulative function. Okay, so here's a diagram just to represent all of that. 160 is over here, so I'm expecting a large probability, a probability bigger than 0.5. And I've put on the arbitrarily large maximum value, which will go into our calculator. So NCD, 160, 10,000, standard deviation, we found that earlier, 8.3, and the mean, 167.68. Into our calculators, and we get 0.8201. That's the probability that for this distribution of the heights of a population of women, that a randomly chosen woman is taller than 160.